Okay, so in view of the fact that some of you are taking the second quarter of 170 concurrently with this quarter, I'm going to very quickly review for you polynomial interpolation, just so that you have a sense as to how we're going to use it later on in constructing numerical quadrature algorithms. So let me sort of briefly state the problem, okay? So you're given a function, say f of x, right? And a set of interpolation points. Let's call them x0 all the way up to xn, all right? And then the basic idea is that you want to find a polynomial Pn of x in the space of degree n polynomials in x, okay, such that Pn of x agrees with f of x at the interpolation points. Okay, so Pn at xi is equal to f at xi for I equals to 0 to n. And so let's think about that for a second. So we know that if you have a polynomial of degree n, there are n plus 1 coefficients. Okay, and then so the condition that Pn of x agrees with f of x at these n plus 1 points, then conceivably it's enough data for you to uniquely specify a polynomial of degree n which has this interpolation property. So the fact that Pn of x agrees with f of x at those points is an interpolation property, and it interpolates f of x at those interpolation points. Okay, so let's try to write down an expression for that interpolating polynomial. Okay, so let's consider what is called the Lagrange form. Of the interpolating polynomial. There are many different possible representations, which if you've taken 170b already, it's you would see, and if not, it's I'm just going to sort of write down the simplest one, which is relatively easy to understand. Okay, so this is the Lagrange form of the interpolating polynomial, right? So I'm going to posit the following form of this polynomial. So Pn of x is going to be some linear combination from, say, I equals to 0 to n of f evaluated at xi, so that's an actual number, multiplied by some polynomial, let's call that L n comma I of x, right, where L n I of x is a polynomial of degree n in x. Okay? All right. And so if you think about this and you want it to satisfy the condition that, again, Pn at xi, is f at xi, then one way to sort of see this, okay, so let's say Pn at xj is equal to the sum from I equals to 0 to n of f at xi times L ni at xj. Okay, so that's what happens when you substitute x equals to xj in this first expression here. and you want this, right? So you want this to be equal to f at xj. Okay, so that's the interpolation condition. Okay, so it's easy to convince yourself that if that's what you want, then you want this L n I evaluated at xj to have a certain property. And the property you want it to have basically is that since you want this kind of condition ideally to hold for any possible function f, and you want to sort of pick these Lagrange polynomials, right, in such a way that they can work with any given function, then what you'd like this thing to satisfy is what's called the Kronecker delta property. Okay, So you have Lni evaluated at xj, and you want it to have the following property. You want it to be 1 if I is equal to j, and 0 if I is not equal to j. So it's easy to convince yourself that if you have this property, Lni, it's like evaluate xj is 1 if I is equal to j, and 0 if I is not equal to j, then this sum collapses to just one term, which is that f evaluated at xj is the only one which is going to be multiplied into 1. All the rest will be multiplied into zeros. And so this sum collapses into f evaluated at xj. Okay, so if you can construct a polynomial with this property, then you're done. Okay, so if you construct a polynomial with this property and you write down this form, it's like which involves linear combinations of these polynomials, it's like weighted by the function values, it's like at the interpolation points, then you've constructed for yourself an interpolating polynomial which has the property that when you evaluate it at the interpolation points, it agrees with the function which you are prescribing. Okay, so that's basically what's going to happen. So I'm going to write down this expression, right? Pn of x is going to be the sum, right, from I equals to 0 to n of f at xi L ni of x, and you want L ni of x evaluated at the point j to have this Kronecker delta property that 1 if I is equal to j and 0 if I is not equal to j. Okay, and I should say that this function has a particular notation for it. It's usually denoted delta ij. So this thing on the right-hand side is usually denoted delta ij. Okay, so that's where we are now. Okay, and we want this to be a polynomial of degree n on x. Okay, so again, it's like you know, we're still in this situation where now Lni is a polynomial of degree n. The n plus 1 coefficients, it's like which allow you to specify this, and you know what the value of this polynomial is at n plus 1 points, which are again the quadrature points. Okay, so let's use that information then to construct this polynomial. Okay, so the first observation is the following, right? You probably know that if you have a polynomial, right, then it is determined up to some constant by its roots. Okay, if you have n roots of a polynomial, then it is well, n distinct roots of a polynomial, then a polynomial degree n is determined up to a constant by its roots. Okay, so recall that if we have n distinct roots, then the polynomial of degree n is determined sort of up to a constant. And I guess I should have mentioned when I was talking about polynomial interpolation that there's an assumption that the interpolation points are all distinct. Okay, it's possible to do interpolation when the points are not distinct, but more or less it's like that gives you puts you in this setting of what is called Hermite interpolation, and you have to instead of specifying just the function values, you have to also add information like the derivatives at the point. And of course, it's like the sort of the extreme case, right, is sort of the Taylor polynomial, right, where the Taylor polynomial involves you giving function information about a function at just one point, but it involves the function value as well as a whole bunch of derivatives. Okay. And if you recall, it's like what was done. It's like in 170b. Then all this fits very nicely into the context of what are called divided differences, which allows you to go from this extreme example, it's like where all the points are distinct, to the other extreme example, which is the Taylor polynomial. The Taylor polynomial, where all the points are the same. Okay. All right. So anyhow, so let's not worry about that for now. Let's just consider the case where you have n distinct roots. N distinct collocation points, n distinct interpolation points. Okay, and if you have n distinct interpolation points, then you essentially know that you have these sort of n distinct roots. It's like of this Lagrange polynomial. So that tells you then that Lni of x, right, is equal to the following thing. It's the product of a bunch of linear terms, x minus xj, for all j not equal to I, right? So there are a bunch of roots, right, at the collocation, sorry, at the interpolation points, and the only one that is missing is the xi term. Okay. So that's what it is, up to a constant. So let's just call that constant c. And the way you determine the constant is that there's a normalization condition, which says that if you evaluate the Lagrange polynomial at the point, the ith Lagrange polynomial at the point xi, then it has value 1. Okay. So you know this from the fact that Lni of xj is equal to 0 for I not equal to j. Okay, so that's the first thing. And you also know that Lni xi is equal to 1, which is equal to c times the product j not equal to I of xi minus xj. Okay, which tells you that c is equal to 1 over the product over j not equal to I of xi minus xj, which when you then substitute back into here, tells you that Lni of x is equal to the product, again, j not equal to I of x minus xj divided by xi minus xj. And again, it's like if the interpolation points are all distinct, it's like then these things are non-zero, and so you have this nicely well-defined polynomial of degree n. Okay, and so this is a polynomial of degree n on x. Okay, so now you're in business, right? So I now know that there's a form which, if this Lni satisfies this Kronecker delta property, then this would have the interpolation property. Okay, and I have an expression for that Lagrange polynomial here. So now I'm in a situation where I can put this all together, right? That if you're given a function f of x and n plus 1 distinct interpolation points, x0, x1, all the way up to xn, then the claim is that Pn of x, which is the sum from, let's see, I is equal to 0 to n of f at xi multiplied into a polynomial, which is this product j not equal to I of x minus xj over xi minus xj, right? This is a polynomial of degree n in the variable x, and Pn of xi is equal to f of xi for all I from 0 to n. Okay, and this is what, and then so Pn of x is the Lagrange form of the interpolating polynomial. And this is the Lagrange polynomial. Okay, all right. So again, it's like this gives you a systematic way of taking a given function, a bunch of points, and then constructing a sort of an interpolating polynomial, which is an approximation in some precise sense of the original function itself. Okay, right. So it has sort of this approximation property, which morally looks a little bit like the remainder term you see in the Taylor remainder theorem. Actually, let me just maybe write it down in the next page once I've said a little bit more about this. Okay, and as we'll see, it's like as the course progresses, the construction of a function which approximates a given function with a certain provable bound on the error you make then allows you to construct algorithms, for example, to approximate the integrals or to approximate derivatives or to approximate solutions of differential equations in a very, very systematic way. Okay. All right. So again, this is the Lagrange form of the interpolating polynomial, and then this is the Lagrange polynomial. Okay. So let me say something about the remainder term. So the remainder term, okay, so we're asking what happens if you have f of x and you subtract off Pn of x, okay? So if you recall, if you had f of x and Pn of x happened to be the Taylor polynomial instead, right, then you might recall that the Taylor polynomial error looks something like f at the n plus first derivative at some unknown point divided by n plus 1 factorial times essentially x minus x0, where x0 is the point which you expanded the Taylor polynomial in to the n plus first power. Okay, all right. So that's actually not okay. So this was in the Taylor case, I guess. Okay. All right, so for the Lagrange case, you have something similar. F of x minus Pn of x is equal to f n plus 1 at some unknown point c. And then c is somewhere in the interval from, so in the convex hull, if you will, of x and x0. Okay, all right. So the way it's like you do this is involves, or the way you prove this, it's like involves sort of integration by parts. It's like together with the mean value theorem, right? Okay. Anyway, and of course applied to the fundamental theorem of calculus, I should say. Okay. So for here, you have something similar. It's like your C is now in the convex hull of x0 all the way up to xn. Okay, and then as you might expect, it's like you're not going to have, it's like an x minus x0 to an n plus 1 term because you have x0 to xn, right? So you're going to have the product from I equals 0 to n of x minus xi. Okay, so that's going to look, so that's sort of the corresponding remainder term. It's like for the Lagrange interpolating polynomial. And again, it looks very, very similar. It's like to what you have, it's like with the Taylor polynomial. So that's perhaps the easiest way to remember this. If you forget the expression for this, it's like you can remember what the remainder term in the Taylor polynomial is and then sort of appropriately modify it in sort of the fairly obvious way. Okay. So anyway, so that's a sort of relatively quick introduction or reminder, it's like of what polynomial interpolation is. And again, the reason why we did this is so that you're sort of reminded of sort of the relevant parts, which we'll then use in setting up some of the numerical methods we're going to talk about next. So let me just stop here.